So you might ask, how can a function fail to be differentiable? We just saw that this function, the absolute value of x function over here, it is continuous everywhere. However, it's not differentiable when x equals 0. So when a function is continuous, it's not necessarily differentiable. The graph of this function has a corner or kink in it over here. So the graph of f has no tangent at this point. So the function is not differentiable here. So it's too sharp to have a tangent. Another way for function not to be differentiable is when the function is not continuous at a. When the function is not continuous at a, then the function is not differentiable at a. So to be differentiable, the function has to be continuous first. So there are three possibilities here. When you have a corner or a kink over here, then this is too sharp to have a tangent. So the function will fail to be differentiable here. And when you have a discontinuity over here, when you have a break over here, then the function is not differentiable over here. And the third possibility is when you have a vertical tangent over here, because vertical tangent, the slope is undefined. Okay, so it's not a real number. Okay, so the duality does not exist. So the function over here is actually continuous at a. However, the limit of the duality, the limit of the absolute value of the duality is equal to infinity. Then you have a vertical tangent over here, and the function will fail to be differentiable over here. So three possibilities: a corner or kink here, or a break over here. So let me write it down for you. So when you have a corner or kink over here, or when you have a break over here, or when you have a vertical tangent. So those are the possible cases. The function will be not differentiable at a over here. Now we're going to talk about higher duality. Okay, if the function is differentiable, then the duality is also a function. So f prime is going to have a duality on its own. So when you differentiate f prime, you put f double prime over here. You see over here, this is f with 2 prime over here. So this new function, f double prime, is called the second duality of the function. So it's called the second duality of this function. Okay. So using Leibniz notation, we can write the second duality of this function as d square here, y over dx square over here. So this notation here stands for second duality of this function. So this is the first duality over here. And when you differentiate this with respect to x one more time, then this will stand for the second duality of this function. Example 6. If f of x equal to x cubed minus x, find and interpret f double prime of x. Now, in example 2, we found that the first duality of this function is 3x squared minus 1. Now we just need to differentiate this one more time to find the second duality. Now we use the definition, okay? So it's the limit of this quotient as x approaching 0. So Up here we have f prime of x plus h minus f prime of x. So we're taking the limit of this quotient. Now this time instead of f over here, we have f prime because we're finding the second derivative, f double prime over here. Now f prime of x plus h here, substitute x plus h into this x. We got this, and f prime of x is going to be this. Now we can expand this perfect square over here. We got this. Now when we do the algebra, we're going to get this. Simplify. Now as h approaching to 0, then this is going to become 0. We got 6x over here. So f double prime of x is equal to 6x. Now we can graph all these three functions together. This is the blue one here is for the function f. The red one over here is for the first derivative of the function. The green one over here is for the second derivative of the function. As you can see here, the second derivative is the derivative for the first derivative. So you see the first derivative over here. It's going to have a horizontal tangent over here. So the second derivative will be equal to 0 here. Now on the left side over here, the slope of the tangent for the first derivative is going to be negative because it is falling from left to right. So the slope of the tangent will be negative. So second derivative will be negative over here. On the other side, the slope of the tangent will be positive for this first derivative. So second derivative is positive over here. We can interpret second derivative as the slope of the curve of the first derivative at the point. Now remember, if an object travels along a straight line, we are given the position function f over here. If we differentiate this one time, we got the velocity function. So first derivative corresponds to the velocity function vt. Now if I differentiate this one more time, I will get the second derivative of this position function here. And that corresponds to the acceleration of the object. That's the acceleration function. What happens if you differentiate the second derivative one more time with respect to t? So we're going to get a third derivative. So you put, this is f triple prime, okay? So what do we call that? That is going to call a jerk. Well, it's going to call a jerk. It kind of makes sense because the third derivative is a rate of change of this acceleration over here. So when you have a big jerk, which is a big change in this acceleration over here, if you are in a car that has a big jerk at that moment, then you feel that the acceleration suddenly changed a lot. So a big change in the acceleration will make you feel really uncomfortable, like a jerk, right? So we call it jerk. And if you differentiate this one more time, you get the fourth derivative. This time we put a 4 here and we put a parenthesis over here. Notice that if without a parenthesis, that means f to the 4 power. With the parenthesis, that means the fourth derivative of the function. All right, so that's the end of this lesson today. So remember, we just talked about the third derivative of a position function is going to, we call it a jerk. And so this is the notation for the third derivative of this position function s over here. So this person, the t-shirt, what does it say here means, don't be a jerk. Now this person is actually an Indian actor who battled depression for long, but unfortunately committed suicide in 2020, in June 2020. So that was a sad story.